Okay, in this problem, I've got a distributed torque applied to kind of a stepped rod here, right? I've got two different diameters as shown here. Everything's steel. Basically, what I want to do is I want to find where the maximum shear stress is in this shaft. Okay, so first thing, essentially what I'm trying to do is I need to find where the maximum torques are, and then from that, I can find the maximum shear stress, okay? So we're going to go through, we're going to do some statics, which is how most things start. So I'm going to draw, say I've got B over here, right? I've got A over here like so. So essentially what I have here is A plus B has to equal that distributed load, right? Those two are balancing that distributed load, which I'm going to keep everything in pounds and inches, so it's just going to be 60, oops, that should be 0 times 20, which equals 1200. So there's one equation, there's my statics equation, but again, I've got two unknowns there, A and B. So what I'm going to use is the fact that the total from A to B, the total twist has to be 0 from A to B, which I can effectively write as, well, there's going to be a twist from A to C, and that has to equal the twist from B to C, right? Basically, it goes from A to C twisted sum, and then C goes back to B in the other direction. Okay. Now, of course, the tricky part here is what the torques are in there, because again, I got that distributed torque in there. This internal torque is going to be easy. That's just going to be A, right? So I can say that's AL over JG. Now again, G is going to be the same, so I'm not going to worry too much about it. Okay, but that's going to be A times its L, which is 5 inches, over J, which is going to be pi over 2. The radius of that smaller one is 1/4 inch, so 0.25 to the 4th. And I'll go ahead and put in G since I have it here, and it's 75 times 10 to the 9th. And that would, oops, not that. 11 times 10 to the 6th. Did the wrong units. Again, I need to use PSI here. So 11 times 10 to the 6th PSI. But again, this is going to cancel out, okay, because it's the same material on the other side. Now, J is different because the radius is different. However, things are very much different because on the other side, I've got to figure out what the torque is going through B. And of course, it changes as I move down. So I'm going to have to do some integration here, okay? So if I look at this guy, at one end it's B, right? And then essentially it will decrease by 60 pounds per inch every inch. So it's going to go minus 60 times x. So when x equals 0 over at the end there, it's going to be B. When x equals 20, it's going to be B minus 120, right? Because x, we're going to say, is going in this direction. Okay? Okay, so when it's 0, it's B, right? And then basically that distributed load is being taken off as I go down. So the torque as I move down is B minus 60x. So using that, I can plug in TL over JG. Okay, but I have to do it in integral form because, again, the torque, T, is a function of x as shown here. Okay, and then that's going to be divided by JG, which will be constant, right? It's constant radius, and it's the same material. So underneath, it'll be pi over 2. This guy's radius is 1/2 inch. Okay, and then it is also 11 times 10 to the 6 psi for the shear modulus. Okay, and again, I have this because the torque changes along the length, and because of that change, along the length, I have to do the integral to figure out, what that torque is, to figure out the angle of twist all the way down that thing. So simplifying this equation, doing some algebra and some calculus on this, the left side becomes 1280 A. And again, I get this, basically I'm going to take the pi over 2 out, I'm going to take that out, and what I'm left with then is just the 1280A. Doing the integral on the other side, okay, I wind up getting 320B minus 192,000. And again, that's that integral. So now what I've got here is I've got two equations, right? I've got my statics equation up here, and now I've got my compatibility equation right here, right? Two equations, two unknowns. From that, I find that A is 120, and I find that B is 1080. Now what I need to do is I need to find the stress in each segment, okay? Because again, what I'm looking for here is the maximum shear stress. So I'm going to find it in each segment. Whichever one's bigger is the one I'm going to use. So start with tau A. Shear stress in A, this is going to be TC over J, where T is 120, C is 0.25. Okay, that's the radius. Okay, and then pi over 2 times 0.25 to the fourth. And from that, I get 4.89 megapascals. Do the same thing for B. I get 1080. Okay, because that's, and again, that's where the maximum torque is going to be. Because at B, it's 1080, right? And then it's minus 60x. So the further away from that I move, I get smaller and smaller torque. So the maximum torque is occurring at point B. Okay, so that's where that 1080 comes from, times its radius, which is 0.5. J on this one is pi over 2 times 0.5 to the fourth. And I get 5.5 megapascals, which is larger than 4.89, so that's the one we're going to circle in. So again, with this one, you do the statics, you do the compatibility equation. Compatibility equation, you have to do a little calculus because of the distributed load, okay? But once I get that equation, then I have A and B. Again, from that, then I can figure out where the maximum torques are in each segment to find the maximum shear stress, TC over J. Again, recognizing that at A and then at B is where my maximum is occurring, using those torques to find the maximum shear stress.